Pedigree analysis is actually not in the AAMC's list of topics that could be tested in biology. However, we are presenting this information here to facilitate your understanding of how genetic transmission occurs, to understand how to write genotypes, and to calculate probability. In pedigree analysis, men and women are given different symbols. Men are typically represented as squares and women as circles. A mating between two individuals is a horizontal line, and children resulting from that mating are presented as a vertical line, connected via vertical lines. Individuals who have a particular condition or the condition we're interested in are typically shaded or colored. So here's a typical pedigree. Questions on pedigrees are typically like, suppose this couple has another child and it's male. What's the probability it would be affected? Or what if this woman married a normal man? What's the likelihood their children would be affected? Or suppose this couple has another child, and so forth and so on. Now, before you can answer any probability questions, you have to learn something about the allele that is causing the disorder. If you don't know anything about the allele causing the disorder, then you can't write genotypes. And if you can't write genotypes, you can't make probability estimates. So let's take a look at the 3 basic questions you have to answer before tackling the pedigree questions. The first basic question is the allele dominant or is the allele recessive? And the way you figure that out is that disorders caused by recessive alleles typically skip generations. So if we go back to the pedigree, now here's what people do wrong. They look all the way across the generation. They say, oh, the disorder is found here in generation 2, and the disorder is found here in generation 3, therefore it is not skipping generations, therefore it's dominant. Don't do that. Just pick one person with the disorder. We'll pick on this guy. And look back at that person's parents. If the person has the disorder and their parents do not, that's a recessive disorder. That's skipping generations. Right? And we can confirm that with anybody else. This guy's got it, his parents don't. This guy's got it, his parents don't. This guy has it and his kids don't either. Right? Kids are not as reliable as going back to the parents, so always go back to the parents first, but this does give us additional information that this is likely a recessive disorder. Second basic question. Is the allele for the disorder carried on one of the 2 sex chromosomes, or is it carried on an autosome? Is the allele sex-linked or is it autosomal? And to figure this out, you count men and women with the disease. And if you have significantly more men with the disorder than women, it means the disorder is sex-linked. And there's a couple of reasons for that. First, if the disorder is carried on the Y chromosome, women never get a Y, so women will never display a Y-linked disorder. Right? And if the condition is carried on the X chromosome, well, men typically have only one X, so they must express whatever they get. You can think of women as having a backup copy, right? Women have 2 X's, so if they get a bad allele on one X, it's likely that the other X will carry a good allele, and they'll be okay. Right? So men basically have 2 possibilities. They can be X good Y, which is not affected, or they can be X bad Y, which is affected. So roughly 50% of male genotypes is going to be affected. But women have 3 possibilities. X good, which is not affected, X good, X bad, which is not affected, and X bad, which is affected. So only 1 out of 3 female genotypes is going to be affected, whereas 1 out of 2 for the men. So if we go back to our pedigree, looks like we have 3 men and 0 women, so this is likely a sex-linked disorder. And the last question is, if the allele is sex-linked, if the disease is sex-linked, is it linked to the X chromosome or is it linked to the Y? And if you want to stop at question 2, having determined that it is sex-linked and automatically say it's on the X, 99.9% of the time you're going to be right. All medically significant sex-linked disorders are carried on the X chromosome. Right? The Y chromosome is very small. Sorry, guys. Codes for like how to make a testis, maybe how to control the remote. That's about it. Right? But the X chromosome is huge. Right? It carries all sorts of genes. How to see in color, how to clot your blood, how to keep your hair from falling out, how to solidify your bones, etc., etc. In other words, it's just far more likely that something will be carried on the X because it's so much bigger and has so many other genes on it than to be carried on the Y. But that said, suppose that a disease was Y-linked. Think about how you might see that in the pedigree. Right? Diseases that are Y-linked will pass from father to son. So if you see a sex-linked disorder that is being passed from father to son, you know that it is a Y-linked disorder. If the disorder is not coming from the dad, then it's got to be sex-linked. It's got to be linked to the X. So in our pedigree here, this guy has the disorder, but his dad does not. That means this is an X-linked sex disorder. X-linked, sex-linked disorder. The only way you get to be a boy is if dad gives you his Y chromosome. So if dad has a bad Y chromosome, you're going to get a Y chromosome. That is bad. Right? So Y-linked disorders show father-to-son transmission, whereas X-linked disorders do not. All right, let's look at a couple of other pedigrees. And then we'll go back and look a little bit at how to write some genotypes. So this pedigree, we're going to start with our first question. Is the disorder carried on dominant? Is it a dominant allele or is it a recessive allele? And so we pick somebody who has the disorder. We'll pick on this person. We look back. Her parents have it. We look down. Her kids have it. Right? This girl's got it and her parents have it. These two kids have it and their parents have it. So this disorder is not skipping generations. So we would say that this is a dominant disorder. And if we count men and women, the second question is it sex-linked? So we count men and women. We've got 4 women and 2 men. So this is not showing a bias towards men. A little bit of a bias towards women, but that's not what we see with sex-linked disorders. So this is going to be an autosomal condition, dominant and autosomal. So first question, is it dominant or recessive? We pick somebody with a disorder. We look back. Her parents don't have it. This guy's got it. His parents don't. This guy's got it. His parents don't. So this is skipping generations, and this would be a recessive disorder. And we see 2 men with a disorder and 2 women with a disorder. So this is equal numbers of men and women, so this would be autosomal. All right, once you know something about the allele, then you can write genotypes. Let's go back to our very first slide, our very first pedigree. We know that this is a recessive, sex-linked, specifically X-linked disorder. So if we look at, we'll say this guy here, men are always an XY genotype, so this guy is going to have a normal Y, and he has the disorder, so he's going to have X bad. And you can swap out bad for whatever allele you want to give this to. So let's say we're going to call A the normal allele and little a the abnormal allele. So then we could replace bad here with just little a. Right? He has Y, X, little a. Right? Recessive allele, abnormal allele. Right, same for any of the other men on this pedigree, the ones that are affected, they're all going to be Y, X abnormal. So let's look at this guy here. He is XY, and he's going to have a normal Y, and he is X good or X dominant, the dominant X, the normal X. Now let's take a look at this woman. She has a son with this disorder, right? So, and she does not have the disorder. So we know that she has at least one good X. So she's going to have X big A. And because she has a son with the disorder, we know she must be carrying the abnormal X. So X little a. We know the same thing for this person, right? She has a son with a disorder, so she's going to be X big A, X little a. Right? This guy is going to be Y, X big A. This person also is the daughter of a man who is affected with a sex-linked disorder. So she does not have the disorder. That means she got at least one good X from mom, and she inherited the bad X from dad. So she's going to be a carrier for that particular condition. Some women we're not going to know. Right? We always know men with sex-linked disorders because they either have it or they don't. So there's only one of 2 choices. But women we're not always 100% sure of. So for example, this woman, right? She clearly does not have the disorder, so she's at least X big A. But we don't really know what she got from mom. She probably got X normal from dad, right? Dad's normal. She's got a normal X, so she for sure got an X normal from dad. We don't really know what she got from mom. She could have gotten the normal X. She could have gotten the recessive X. So we're not sure what her genotype is. Right? It's a 50% probability she's completely normal. It's a 50% probability she's got a bad X and is a carrier. Same for this woman, although this woman married into the family, and often people who marry into the family are completely normal. And usually that's a safe assumption, because a lot of times you're dealing with recessive, not recessive, but rare disorders, and somebody who is randomly marrying into this family is unlikely to be carrying the same rare allele that the family is. Right. So it's a safe assumption she's X big A, completely normal, but we're not 100% sure on this either. So this is how you want to write your genotypes for sex-linked disorders. Make sure you're including the Y and the X, or the X and the X for women, so that you do not accidentally give the man an extra allele. If we look at our other pedigrees, right, our dominant autosomal disorders. So we look at this person. We'll start with somebody who doesn't have the disorder. This guy does not have the disorder, and this is a dominant disorder. So the only way you can not show the disorder when it is dominant is if you are homozygous recessive. So he has to be little d, little d. Notice we're not going to use an X and a Y here because this is not a sex-linked disorder. He's going to have two alleles, one on each of his homologous chromosomes. Now, this person here, she clearly has the disorder, so she's going to have the dominant allele. And then we can look at her kids. If she is homozygous dominant, if all she has is dominant alleles, then every single one of her kids would inherit a dominant allele and have the disorder. But we see that 2 of her kids have it and 2 of her kids do not. So these kids got a little d from dad, right? That's all that dad has to give them, and must have also gotten a little d from mom. So this person must be heterozygous. All of these kids, the ones that are affected, are going to be heterozygous as well, because everybody gets little d from dad. The question is, what do they get from mom? So she has the disorder, so she must have gotten big D from mom. This guy got little d from dad and does not have the disorder, so he must have gotten little d from mom as well. And same reasoning for our second generation here. We can do that for, right? All of these people are little d, right? This person married in. She does not have the disorder. She's got to be little d. This person's, we're not sure what this person is. This person got little d for sure. Oh no, this person is little d, right? Never forget that, which I just did. Dominant disorders, the only way you can not have the disorder is to be little d. Right? Homozygous recessive. All right, last one, autosomal recessive. We'll pick on somebody who does not have the disorder. Right? We'll start here. And in order for somebody to have a recessive disorder, they have to be homozygous recessive. So this person here is going to be homozygous recessive, little d. Which means that she had to get little d from both of her parents. So both of her parents have to be carrying little d. However, they are not affected by this disorder, so they're going to have the normal allele, the dominant allele, along with it. Same for this guy, little d. This guy got lucky. He got big D from somebody, either mom or dad, and he's either homozygous dominant, big D, or big D, little d. All we know for sure about this guy is he has big D. Same reasoning for the other generations, right? This person here is also big D, whatever. The fact that none of his kids have it suggests that he's not carrying this disorder. Now, this case, this person has the disorder, so we know she's little d. Now, we can go back and clarify then, this guy is going to have little d, and the person he married is going to have to be heterozygous as well, right? So we can sometimes get information about people who married in based on what their kids are. Let's review what we talked about in this video. We discussed the pedigree symbols. We looked at the 3 basic questions to learn something about the allele causing the disorder and to learn how to write the genotypes, and then we spent a little bit of time learning how to write those genotypes.